Hello again, everyone, and thank you for attending today's webinar, Simulation with Nonlinear Structural Materials, brought to you by Design World Magazine and COMSOL. We would like to thank our presenter, Mateusz Streck, Technical Product Manager at COMSOL, for being here today. I'm Leslie Langnaw, Managing Editor, and I will be your moderator. Just a couple of housekeeping details before we get started. If you wish to tweet about this webinar anytime during or after, you can use the hashtag DWWebinar to tweet about it. This webinar is being recorded and it will be available to you at our website, designworldonline.com, tomorrow, and also we will email you a link about that. We will also have a question and answer session at the end of the presentation, but you can go ahead and submit your questions now. You'll see on your control panel that there's a spot for you to put in your questions, so feel free to put them in anytime during the presentation. Now I'd like to introduce you to Mateusz. He works as the Technical Product Manager for the Fatigue module at COMSOL. He studied aerospace engineering at the University of Michigan and vehicle engineering at the Royal Institute of Technology. In 2008, he completed his PhD in solid mechanics at the Royal Institute of Technology. Before joining COMSOL, he worked at SKF's European Research Center as a researcher and project leader. And now I'm going to hand over the microphone to Mateusz.
Yeah, thank you, Leslie, for the introduction. So today we're going to talk about nonlinear structure materials. The agenda for today is as follows. We'll talk about modeling with COMSOL Multiphysics, and then it's time for today's main topic, simulation with nonlinear materials, complete with applications. A live demonstration will follow of how you can set up and solve a model of a pressurized elastoplastic orthotropic container. Finally, there is the Q&A session followed by a brief how-to. We encourage you to submit questions at any time during the webinar. You don't have to wait until the Q&A session starts. So, why model with nonlinear materials? Well, why model anything at all? If you are going to create a new product or process, hyperelastic seal or reinforced concrete, you first want to get the concept right. The most important decisions are often made early in the product development cycle, when multiphysics modeling can give you the valuable insights you need. The benefits of multiphysics modeling extend easily to the design and optimization of the product by reducing the time and money spent on prototypes. And if you integrate multiphysics modeling with manufacturing and quality assurance, you'll end up with a product that's much better understood and better characterized. It's clear that the simulation can help you through the product development cycle. Let's look more specifically now at how simulation in the COMSOL environment. COMSOL is a multiphysics as well as single physics simulation platform. It covers mechanical, fluid, electrical, and chemical simulations, or really any physics that you can think of. COMSOL is particularly well known for multiphysics or coupled phenomena. By this, we mean that two or more physical effects that interact with each other and without limitations to the number of physics that can be included in the model. This is particularly advantageous in modeling of nonlinear materials. You can combine the things you learned today about structure mechanics, which for example heat transfer, to see how plastic or creep strains affects the performance of your devices. We also notice a lot of users enjoy the benefits of staying in the same environment for single physics simulation as well. This allows you to use the same workflow no matter what the task is. One of the greatest strengths of COMSOL is that it's strategically designed from the ground up to enable cross-disciplinary product development. To put it simple, COMSOL enables you to consider the phenomena that influences how your product or process performs, and then helps you to improve it. One structure application where physics coupling must be considered is a solar panel subjected to wind loads. The support of the panel will bend with the flow and alter the flow that will in turn affect the panel with a different force. Here we need to solve for fluid velocity, field components, and structural displacement in the same study. Now, let's explore the COMSOL desktop. Our interface is quite straightforward to use, where all the modeling steps are documented and can be edited later on if needed. This actually happens in the window referred to as the model builder. We input or select our custom settings in the window just next to the model builder, and then visualize our results in the graphics window. And here's the COMSOL Multiphysics product suite. All products can be used together to create many unique physical couplings. And as you might have noticed, we can interface with different CAD formats, with different software packages and programs for data organization and visualization. Today's webinar will describe functionality in COMSOL Multiphysics used in combinations with the Nonlinear Structure Materials module, with the Geomechanics module, and with the Structure Mechanics module. So why do we use the nonlinear structure materials? Well, it's very simple. We want to capture material behavior of real materials. And many times, the linear behavior is not sufficient, and we need to move into the world of nonlinearity. The nonlinear structure materials module provides COMSOL users with some predefined materials. They are found in the family of creep models, Hyperelastic, Elastoplastic, and Viscoplastic. In the figure in the middle, you see what happens when you have a hyperelastic material. It behaves severely non-linear when you load it, and then upon unloading, it will follow the same path until it's stress-free. When you deal with plasticity, upon loading, you will get some permanent strains, some permanent deformations, and then upon unloading, it will unload linearly, so that you are left with some permanent deformation. When it comes to soil and rock and concrete models, a user have option to choose them in the geomechanics module. Those models, they are suitable for compression. In the column to the left, you see which predefined creep models are implemented in the COMSOL Multiphysics. They all depend on the inelastic strains that are time dependent. Additionally, you can also calculate the creep dissipation. The example on the right-hand side is a rubber cap. It consists of two material models that are combined. You can see it as a primary and secondary creep. The first one is Norton, and the second one is the Norton-Bailey. The Norton-Bailey has a time shift implemented, and upon loading, you're going to get a certain stress distribution. Here, the red color defines the peak stresses. So we assign inner pressure, and then you can see that the stress decreases when you go further out. And then with time, different mechanisms will kick in, and the highest peak stresses, they will move further and further away from the interface where you apply load. The hyperelastic model, they depend on energy, energy formulation. Here again, there's many models which are implemented in nonlinear structure materials module. Additionally, there are three monorivelin type monorivelin models, the 2, 5, and 9 parameters. The example of this type of models is the rubber velocity joints that undergoes severe deformation, but upon unloading, it will go to a stress-free state. When it comes to plasticity, we will be left with permanent strains. This type of materials is frequently seen because most of the materials, they have some nonlinear contribution. The onset of plasticity is defined with different yield criteria, and we have 3 which are implemented. Of course, the user have a possibility to prescribe its own criteria as well. There is also a possibility to define different hardening options. The most frequent one are implemented, and also decide which kind of plastic flow we want to model. There are certain possibilities to alter those material models with the user-defined models. Basically, wherever you can type a number, you can type an equation that depends on different variables. The application of those models is shown to the right, where a stent is deformed with the balloon that is inflated inside of it. This stent is put in the human body. You inflate the balloon, and this stent is expanding in aorta in order to improve the blood flow. What you can see that there will be some high stresses where you have the permanent deformation of the stent, and that's what keeps it in place. When it comes to time-dependent plasticity, there is one model implemented in the COMSOL. It's called the ANAN. This type of materials is found, among others, in the solder joint in the microelectronic industry. The solder joint connects the electronic components to the printed circuit board. And here you can see what happens when you apply the temperature, how the creep develops, and you can also calculate what kind of what kind of creep dissipation you will have in this type of applications. When it comes to the concrete and rock models, they are predominantly used in the compressive loading. There are different types of models, and one option which the user can use is that you can provide a tension cutoff to those materials. The application, which is shown to the right, shows reinforced concrete. The long bars are the steel bars, and then the rest, the matrix material, is the concrete. Here you connect 2 different types of elements. The bars, they are modeled with truss elements, which can only take axial stress, while the 3D elements, which are modeling the concrete, they can take stresses and strains in different directions. But with the COMSOL, you can connect those different types of elements since they share different nodes, and you can get the accurate stress description in both types of materials. Another family of materials are the soil models. The difference between soil models and the rock and concrete materials is more on a phenomenological level. They are defined with similar equations, but soil models are more used for ductile material, while the concrete and rock are used for the brittle material. The predefined materials are shown in the left column, and here for soil we have additional options to have a compressive cap and tension cut off. The example shows what happens when you excavate a tunnel. The soil will undergo deformation under its own weight, and then once you if you remove the ground and create a hole, and you put some kind of top pressure, there will be plasticity developing around the hole. The way materials are defined in COMSOL, they are added to the tree of the physics. Here you can see that there are 2 different materials which are added to the same model. One is linear elastic with plasticity, and second one is the hyperelastic. And what you can do is that in the same structure you can prescribe different types of materials. Once you go and click on the material, you're going to get the window that displays the modeling option. On the top, you will see the equations, and then the different options for the modeling will follow. Here for the plasticity, we have small plastic strains, we have the yield function, and then some other materials. What you see here, for example, for the isotropic tangent modulus, there is a possibility to take it from the material. And materials are defined in the tree, where you can prescribe different material properties. But you can also change this and type the equation or the number directly. Wherever you can type a number in COMSOL, you can type an equation, so that this, for example, isotropic tangent modulus can depend on other parameters. I think probably a better example is the yield stress, which frequently depends on the plastic strain. So here you can actually type the yield stress as a function of the plastic strain or another variable. COMSOL provides the geometry import from other softwares. For external import, we also have some defeaturing options, and this is especially handy where there is some kind of unwanted information that follows from one format to COMSOL. Then you can deselect the unimportant features so that you will get a much better mesh on your model. Besides the import from other materials, COMSOL has also own geometry operations where you can create with different actions, different shapes and different geometries. For those cases when you need to interact with different physics, COMSOL have also predefined interfaces. For example, the thermal stress couples the structural behavior with the thermal behavior, so that we can prescribe both mechanical loads with thermal boundaries. Joule heating and thermal expansion is another example. Here, the electric current, electric field will cause the temperature change that will cause strains in the structure. This multiphysics interface is, for example, interesting when you deal with the microchip industry and when you put the current through solders. Since those materials are nonlinear with different creep mechanism, they will change their shape under the temperature change. And yet another coupling is the piezoelectric devices. Here, the electric field have a direct influence on the displacement or the stresses, and vice versa. When you work with nonlinear materials, you can enter into large deformations and large rotations. Then to work with the small stress or displaying stresses or strain measures in the original configuration is not sufficient, and you need to display with respect to the new deformed configurations. And for that purpose, we have different stress measure and strain measures which are predefined. An example of such is the green Lagrange strain. We also can calculate strains in different ways. With the small plastic strains, we have the additive decomposition of strains, and this works in many cases. But when the strains becomes big, or where your models they rotate, you have to consider the nonlinear effect in the definition of strains. And for that purpose, we have the multiplicative decomposition of the deformation gradient when you use the large plastic strains option. The difference between those two options is shown in the graph that demonstrates what happens in a tensile experiment. You have a round bar, and then you pull in two different directions. After some time, there will be necking occurring in the central section of the of the bar, and the radius over there will decrease. If you use the small plastic strains option, you will have a linear relation between the displacement which you apply on the top and then strains in the middle of the section. Then you will not be able to simulate the effect of necking. However, if you use the multiplicative decomposition of the deformation gradient, you will capture the necking phenomena, and you can see that for a certain displacement, there is a huge difference between those different strain, those two strains defined with different ways. In modeling, there are different options. You can enable plasticity in subdomain. This is especially handy where you work with models where plasticity occurs locally. When dealing with plasticity, you add extra degrees of freedom to your model that the model needs to be solved for. And imagine that only 2% of your model undergoes plasticity and they need to have those degrees of freedom. If you prescribe plasticity to the rest of your structure, you will end up with a zero value strains. And if you know it already from the beginning, you know that there will be linear behavior there. So there is no need of prescribing plasticity everywhere. So by the composition of your structure into subdomains, you can actually save a lot of computational time. Moreover, when you model with nonlinear materials, you can add different effects to each other. For example, you can have plasticity and creep work together, or you can have different creep effects in the same model. Also, you can add the thermal expansion, creep, or plasticity with each other. And in case you have a material where the principal orientation of the material follows the shape, like for example here it's a rolled steel in the container. In this case, the stronger dimension is out of the plane. You need to rotate the orientation of the material, and this is also possible in COMSOL Multiphysics and will be demonstrated later in the live demo. For creep and viscoplasticity, basically those models are quite similar. In the viscoplasticity there will be some hardening, and in creep there will be no hardening. Those two names are used, but numerically those two models are very similar. So in creep you can combine different creep effects with each other, and you can also prescribe your own creep rate tensor. And again, as you see here, since you can type a number, you can also type a relation, so that you can have creep depending on stresses or some other variables that can be calculated in the COMSOL Multiphysics. In soil plasticity, the options they give the user a possibility to limit your yield function. If you go in the compression in the hydrostatic space, at some point you want to limit it, and for that purpose there is an elliptic cap which you can put over your yield surface. And if you want to cut it in tension, you can also specify it with a certain relation. The dilatation angle allows you to orient your yield function in a certain direction, and we have also a parameter match to the Moore-Coulomb equation. The hyperelastic materials, for the hyperelastic materials, we have the nearly incompressible option. Then you can separate the energy function into two contributions. One is isochoric and one is volumetric. This prevents locking when you come to the nearly incompressible situation. And the functions they can be defined as a function of any variables which you can calculate in COMSOL. In case you deal with materials where the inelastic strains are calculated with different relations than those which are defined in the module, those materials can be different brittle materials, or for example the Ramber-Osgood material that experience plasticity at already very small stresses. You can prescribe the inelastic strains with help of the initial stress and strain, which is a subnode to the linear elastic material. In those cases, you create your own degrees of freedom that calculates the inelastic strains, and those degrees of freedom are added to the model via the initial stress and strain node. The functions for material parameters can be also can be dependent on different parameters. Here you see an example of how yield stress varies with the temperature and with the plastic strain. When the plastic strain increases, the yield stress increases, and when the temperature increases, the yield stress decreases, which is observed in reality. You can have functions that depend on more parameters. Here, however, the example with 2 is only shown because this can be visualized with a 2D plot. This material is used in the example where a pressure vessel is subjected to an internal pressure, and where a hot environment suddenly becomes cold. In case of emergency, there will be cold water coming into the smaller pipe, into the bigger pipe, and there will be some thermal stresses around. The material consists of two, or the structure consists of 2 materials. There is one which is going around, it's very thick, and then you have a cladding on the inside, which have better properties against the corrosive environment. When dealing with soil, many times you are faced with models which can be really big, while your deformation occurs locally. For example, if you have a slice of ground and you want to see what happens when you compress it in one point, the question is how far should you model in order to avoid the boundary effect. Since you don't want to model very large structures, this increases the computational time. You can display the end of your model with infinite element domain. This is utilized in this model where you actually have a very long slice that extends very far, and you want to compress it locally. You can then create a model of the soil, and then towards the end apply the infinite element domains. You prescribe the length of it, and then you can also apply different boundary conditions on the edge, and those elements will take care of what happens from here on until very far away. This is also shown in this example. So there is a deformation taking place centrally, and then there will be a slight tilting of this line here, while there is a roller conditions towards the end. This is not shown in those elements because stresses cannot be displayed in this type of elements. All different models which have been mentioned in this presentation can be also found in the model library. There we provide the user also with the step-by-step instructions how to perform this type of analysis. 2 model libraries of interest are the geomechanics module and the nonlinear structure materials module. There you have about 30 examples that demonstrates different phenomena. In the column, there is just few models mentioned, and what you can see is that the models, they deal with creep, with bioengineering, with hyperelasticity, plasticity, viscoplasticity, and then with soil models and some concrete models. Also in the step-by-step instruction, you can find different modeling tricks which can help you to model your application. And by this, I would like to move to a live demonstration of an orthotropic container. The container can be seen in the picture on the left. It's a pipe that is that ends on both ends with half spherical caps. The pipe is thin-walled. And due to symmetry, we're only going to model 1/4 of the model, and we're going to utilize the 2D axis symmetry. What's interesting with this pipe is that it follows Hill orthotropic plasticity, and it has one direction which is oriented, or it has material directions which are oriented along the geometry, so that the out of plane direction is the strongest one, and as you see, this direction needs to change orientation when it goes along this arc. Here it will be constant. So I will move to the COMSOL desk, and I will show you how to model this type of application. All right. So let's model this application in the COMSOL Multiphysics. This orthotropic container will be modeled with the 2D axis symmetry, and I will utilize the solid mechanics where I will ramp up the load via or pressure via stationary study. By selecting this, you get certain nodes in our modeling tree which are predefined. You can see that one of them is for the geometry, and I will just change it to centimeters before I create the geometry. By right-clicking, you get the different options to create your geometry, and since it's very simple, you can simulate it with help of circles and rectangles. I will create a circle sector of 90 degrees for the top cap, and the outer radius is 26 centimeters. The inner radius is 24 centimeters, and here again I need a circle sector of 90 only. Since I want to take a difference of it, I use the Boolean operator difference. I add the bigger circle or circle sector, and I subtract the smaller circle sector, and I build it. The second part of the geometry is this pipe. I use a rectangle with width of 2 centimeters and height of 40, and I position it at 25 and minus 20. And the center should be there. So by pulling this, I get the zoom extension. So this is how the geometry looks like. The line here indicates that this is axis symmetry. I will move to the physics, and now I will prescribe pressure. By right-clicking, you see the different options which can be applied. Those with the full symbol, they demonstrate what you can do on the domain level, while those with this pink line demonstrate what happens or what kind of conditions we can prescribe or on the line. And since I have pressure on the inner wall, I want to prescribe it on the line, and I have boundary load. I select my boundaries, and I want to define it as a pressure. Since I want to ramp up the pressure in the analysis, I will call the pressure P with the variable named pressure. Now, when you move away, you see that it became yellow, and it means that the software doesn't recognize this variable, and that's true. We haven't defined the pressure anyway. So I will go to the global definition, and as a parameter, I define a pressure, and I will assign a value of 0 megapascal. Within the square brackets, you can type a unit, and the COMSOL will recognize All right, let's move back to the boundary load, and you see it became black, which means that the COMSOL now recognizes this variable. I want to prescribe the constraints. I will apply a roller condition for the symmetry on this side in order to mirror what happens on this side into the bottom side. So now my loads and boundary conditions are prescribed. So let's move to the constitutive behavior. It's orthotropic. The role is orthotropic with plasticity. So we need to add plasticity into the linear elastic material. As you see, a subnode gets immediately the selection of the top node, and here we have some certain equations which describe our model. This just shows that we have plasticity, and then you have a different options in this model. I want to use the Hill orthotropic plasticity as a yield function, and now I have an option to define material parameters either from materials, it will be from this node, or type it directly in here. But I will define the material. For the hardening, I use the perfectly plastic. And now I need to prescribe the different material parameters. So I add the material, and the COMSOL directly senses which kind of material parameters have not been defined, and it populates a list with those parameters. The Young's modulus is 210 gigapascal. Poisson's ratio is 0.3. Density is 7,800 kilogram per meter square. And for the initial tensile in shear yield stresses, the values are follow. I will define the first and second direction to be the same, and the third one will be the one which will be coming out of the structure. So the in plane normal yield stress is 381 megapascal. We have two directions, 361. Then the out of the structure is slightly stronger, it's 140. And then we have shear, which are 240. This is the direction which is shared with the out of the structure direction. So there are 240. And then the last one is 220. Just to see that everything is correct. E6, E6, E6. That's correct. So the materials are now prescribed. But what we need to do in the following step is that we need to prescribe a new base vector system in order so that the material follows the shape of this pipe. This is done in the coordinate system section where we have base vector system. As you can see, there are two new base vector system, x1 and x3, and they are functions of r and z. I will not go into details, but it's basically a function of sine and cosine. This one will be sine at r. So I'm typing the equations directly. It's a sinus, and then I will take the tangents in order to rotate it, and then I prescribe a Boolean operation dom equals 1 because this is a domain. So this equation will be valid only on this domain, while this will be will give 0. Here it's on the other hand with minus cosine, and then we have a contribution for the second domain. Here the one direction is going down, so that's we have the minus sign. I will copy this. This we only change the cosine, and then the 3 direction goes in the positive r direction, and then finally we apply sine to the last field. Now we need to prescribe it, and we can also add the bet mesh. We're gonna have a map mesh I want to have a distribution through the length with 5 elements because there will be gradients going out, and I will add a distribution on those 2 lines. I add 15 elements, and I have predefined. And then finally on the top one, also I put the aspect ratio to have better elements close to where the plasticity will take place. Now the model is ready, so let's ramp it up. Since the analytical solution to this problem, or approximative analytical solution to this problem, is 36.5, I know that the model will behave linearly until that level. However, I take one step until 31 megapascal, and then I take smaller steps to see how COMSOL captures this transition. And once this is done, I can compute the solution. The progress bar shows how the solution goes on. You get the information about how many degrees of freedom, and after a few seconds you get a solution. When you solve this this model, you get the stress variables in your solution. The predefined stresses are the predefined plots shows stresses. This displays what happens for those different steps. The other defined plot is the full 3D. You can also display different information. For example, if you want to see how the plasticity develops, you can use a 2D plot. You can duplicate this one, and you need to prescribe different variables. This is effective plastic strain, and you can plot it and you can see what happens. This deformation is performed with magnification, but if you zoom in, you see that there is a plastic deformation occurring in the centrally in the pipe, and it was wise to take a mesh with that goes through the thickness, because you see that there is a nice gradient here. What's interesting to see is when the plasticity starts to develop, and for this purpose you can perform the surface integration, which is found under the derived variables integration, surface integration. For that you have a window where you have to specify certain things. You define your domains, and you type your equation, and also here you can compute volume integral. This is not the volume integral, not necessary for the computation, because you just want to have the onset. By clicking evaluate, you're going to get a list, and then you can create a plot out of this, and you see that the onset of plasticity starts at about just below 36 megapascal, which was predicted by the analytical value. So by this, I will end this live demonstrations, and let's hear for some questions. So have we received any questions?
Yes, we have. Hi, Mateus. This is Lance Brown. Leslie seems to be having some audio issues. So just while she's redialing in, let's go ahead and I'll go ahead and ask a question here for you. So the first question I have, what kind of variables can be evaluated in COMSOL?
basically any variables which you can type an equation for. In structure mechanics, most of the variables, they depend on the displacements. Displacements are transferred into strains. Strains are transferred into stresses. Stresses are transferred to something else. And wherever you can type a relation, you can display it in COMSOL. Also, you can create your own variables that, for example, depend on partial differential equations or ordinary differential equations. You do it in a separate physics, but then you can display it. So different stress measure, strain measure, whatever you can type.
Great, thank you. Another question we have is, can COMSOL visualize different stress measure?
Sure. It's important to visualize stress with respect to different configuration dependent on your applications. And for that purpose, we have those variables predefined in the Nonlinear Structure Materials module.
Thank you. Another question we have is, in a model containing primary, secondary, and tertiary creep, can you display the different creep strains?
Sure. You can separate the contributions of different creep models from each other. I think also we have models in our model library that demonstrates how this is done.
Thank you. Another question here is, can COMSOL simulate damage in constitutive models?
There are limitations to how you can model it. So we can do it to some extent, but with limitations.
All right, now how about, can users implement plastic material models with different variables?
Sure. There is also a possibility for this in COMSOL, but just to let everybody know, not anything. Not everything what can be created. There are some limitations. It needs to follow the syntax which is used in COMSOL. For example, if you have some internal variables which can be defined with PDEs or ODEs, then you can create an additional physics where you calculate this variable, and you can calculate strains, for example, in the structural application by use of those variables.
Thank you. Another question we have here: can COMSOL simulate fatigue?
Yes. For that purpose, we have an own module which actually I'm responsible for, and in the fatigue module we have possibility to work with critical plane models, which are very time-consuming from the calculation point of view. However, by using of multi-threading, this analysis becomes quite quick because this computation is spread on different processors. Moreover, there are possibility in the fatigue module to perform a combined study where you perform a rainflow counting with Palgrim Miner. And with the coming release, we will be able to calculate with the thermal fatigue that actually incorporates the nonlinear behavior such as creep or plasticity.
Great, thank you. So really quickly, it looks like we may have gotten Leslie back up online here. Leslie, are you there? Oh, maybe not quite yet. All right. Well, continuing on. Could you, this person asked, could you please elaborate more about the interfacing capabilities?
Sure. First of all, there are several products which can be shown. I think if you push the slide to the next one, we will be able to see which kind of products can be seen. So just push to the next slide. Here, in the right on the right side, you see all those different boxes with yellow bar, and this shows which kind of CAD interfaces or different products where we can have live link. And with live link, it means that you can actually still be in the product, perform a COMSOL analysis, be in the product which you are using, alter it. The product by the live link will alter the COMSOL model, which then can be solved, and you can display the results in the product with, where you are working. For example, imagine in the Excel you have your model. Via the live link, you connect the two programs together. You work in the Excel. You take the control of COMSOL via Excel. You can parameterize your model that communicates with COMSOL.
Muted.
The model is solved, and you have everything in one environment. And for the
Unmuted.
yeah, we have a different with the different products. And then once you import your geometry, you will also be able to use some deferring features in order to hide certain unwanted effects from the other program.
Thank you. Yeah, so just really quickly, you have some people inquiring about questions that they've sent that we may have passed over. Unfortunately, we are receiving dozens of great questions, and we're not able to get to all of them. So we're just kind of picking some key questions, but COMSOL and representative from COMSOL will get your question. They can follow up on an individual basis. With that being said, I believe we do have Leslie online now. Leslie, are you there?
I am back on. Yep.
All right.
What was the last question that you asked?
The last question that I asked was, let me just get it here, was please elaborating on about the interfacing capabilities.
Okay. And let's see.
So I believe we've almost exhausted all the questions that we can come to. Looks like there's one more question that's under review. So, but with that being said, I will go ahead and turn the mic back over to you, Leslie.
Thank you. Okay, so one person is asking that they were simulating amorphous silica structures, and how would they know what kind of model to select?
Well, that's a good question. I think to answer this question, you need to think how your model behave, like phenomenologically, and see if there is some kind of representation of this model from the equation point of view, and then by seeing it, you can see what kind of materials models we have in COMSOL, and it might be so that one of them is actually what you are looking for. But since material models, you have so many. In the presentation, we went over creep, plasticity, hyperelasticity, rock, and concrete. All those models, they have different behavior, different nonlinear mechanisms. So I just suggest that you look into your equations and see if there is something that we have. If not, if you can define the model or the inner variables with, for example, with some inner variables that changes with time, you can incorporate them into an own ODE, and then you can add, for example, strains via the initial strains into the COMSOL material.
Okay, and I believe that's all the questions we have for now, or time that we have for questions for now. But Mateusz, I believe you're going to give us a little bit of information about COMSOL now.
Sure. We're going to move on to the following slides, and the question that we hear quite often from the audience was about how to try out COMSOL Multiphysics. One way is to join us at the workshop. Our workshops are free hands-on events where you can meet a COMSOL specialist and try COMSOL Multiphysics with their guidance. The list of different workshops can be seen on this slide. Workshops in North America and Europe, and we also have workshops in other places of the world as well. You can also register to attend the COMSOL Conference 2013, which we are hosting in Boston, Bangalore, and Rotterdam during the month of October. Also during that time, you're going to see what are the news in the new version of COMSOL, because it will be released in a short time just before the conference. Or conference includes hands-on mini courses, demonstrations, and presentations by COMSOL users, making it an excellent way to get in-depth information about COMSOL Multiphysics and its main capabilities. For more information about the conference and to register, please visit www.comsol.com/conference. And there is helpful information available about multiphysics, COMSOL, and our products on our website. You can find user stories, a model gallery, discussion forum, and much more. And you can contact us at the link www.comsol.com/contact. And the webinar has now reached its conclusion. Thank you very much for attending, and have a great day.
And just a reminder to everyone, this webinar will be sent to you tomorrow, and it will be made available on the Design World Online website. If you have any questions that you would like to discuss among yourselves, you can also do this on our engineeringexchange.com, which is a social media forum specifically for engineers. We would like to thank COMSOL again for this presentation, and we thank you all for attending. Have a great day. Bye-bye.